Heavenly Father, we thank you for this morning. Thank you for these students. Just pray with us, help us to understand a little bit more about Lagrange multipliers, and we just ask that you be glorified in what we do here this morning, Lord. In your name I pray. Amen. All right, so let me state again the problem. We wish to find extrema for, let's say, f, which is a function from, let's say, Rn to R. So it's a real valued function. This is what we typically call the objective function. Our objective is to make that as big or as small as possible. All right. We wish to find extrema for this objective function subject to constraints. It could be plural, and we'll package the constraints as a level surface. So basically, g of Rn goes to, let's say, Rp. So this is P constraints. Right, so this, in particular, let's suppose that g of, I don't know, what do I want to use? G of x is equal to C is the constraint surface. Maybe I should say constraint manifold, since it may not be two-dimensional. Sometimes I try to use the word surface as a two-dimensional manifold. All right, but on occasion I'll slip up and use it in a more abstract sense. So this is the problem. And let me just draw a picture for you of what's going on. So, here's Rn. Right, n dimensions. And then let me give this thing a name. Let me call it M. So here's the constraint surface, right, M. And the method of Lagrange multipliers makes a huge assumption at the start of everything. It assumes that there is a solution, all right? So suppose that there is an extremal point. Suppose you have some point in Rn which satisfies the constraints and is a maximum, right? If you think about that, suppose that point is P, right? So assume f of P is local extrema. Or a local extreme, if you like. Then what can you do? Well, the story that gets played out again and again as you study abstract analysis is you can use curves to find the information you need about a given problem. And so if we look at curves through that point, we can actually learn what the relation has to be between the gradient of the objective function and the gradient of the constraint functions, right? So this g, by the way, is what? To expand it, that's actually g is equal to what? It's g1, g2. How many of them? Yeah, gp. And I'm assuming that this constraint has rank p. So I'm assuming that I have p independent constraints for the sake of, well, not putting more fine print. Okay, so picture it. You got some curve, right? Right? And so at that point P, we can look at, let's call this curve gamma, right? And at the point P, we have a tangent to gamma, right? So there you'd have gamma prima, and we can assume that gamma of 0 is equal to P without loss of generality, right? If gamma of something other than 0 is P, just shift the parameter, shift it to 0, okay? So there's no loss of generality there. Suppose we have P is given by gamma 0. You got a tangent vector there. So if I look at, one thing I can look at h of t. defined by f of gamma of t, right? I can look at this function. So what is that? I'm just feeding the objective function to the curve. I'm assuming, of course, what else do I know about? Well, one thing at a time. So this function here is it's a restriction, right? It's a restriction of the objective function to the curve. What can you say about h of 0? H of 0 is what? It's the extreme value, right? H of 0 is f of gamma of 0, which of course is f of p, so that should be an extreme value. And h is a function from what to what? It's a real valued function of a real variable. So what we learned in Calculus 1. Remember? If it's an extreme value, h prime of 0 must be what? H of 0 is, extreme is an extrema. Again, using Calculus 1. But what else do you know? What's ddt of h of t? Which is what? That's the gradient of f at the point gamma of t dotted with the gamma dt by the chain rule. And that's 0. Well, that's not 0 generally speaking. That's h prime of t, right? But h prime of 0 is the gradient of f at the point p dotted with gamma prime of 0, right? That has to be 0. Geometrically, what does that say about the tangent vector to the curve? Or more specifically, what does that say about, if you look at the point, let's say p comma the gradient of f at p, what can we say about this vector? Is it in the tangent space at p, or is it the normal space at p? The what? It's the normal space, right? So this says that it's the dot product with a tangent vector is 0. So it follows that this vector is in the normal space at p to m, as we talked about the other class. You guys, so far so good? That's the one big thought. That's big thought number 1. Well, this is the major thought for today, yeah. But don't worry, I have more thoughts. Point number 2. What's that? Yeah. The gradient of f has to be in the normal space if it's the. But on the flip side, right? I guess here I'm just really deriving things I've talked about last class, but for the sake of this argument being self-contained, let me also include this comment here. We also know that g of gamma of t is what? It's equal to c, right? Because the curve is on the surface, right? On M, it's on the constraint surface. And if I differentiate this with respect to time, what's that give me? G prime of gamma of t times gamma prime of t, right? Equals to 0. Now, technically speaking, that's the 0 of size p, right? And if you expand that, what's that look like? What's this? It's a stack of gradients, right? In my current annoying formalism, what do I have to say? I'm missing something at the moment, right? Transposes, right? To make them row vectors. And so what does that say? Gradient of G1 at P dot gamma prime of 0 is equal to 0, and so forth on down the line, right? The gradient of GP at P dotted with gamma prime of 0 is equal to 0. Of course, this shows you something I already told you last class, which is that the gradient of G, let's say J, at the point P, attached to the point P, right, is an element of the normal space at P to M for each J. So the gradient vectors to the constraint functions are going in the normal direction, right? But also the gradient to the objective function is going in the normal direction. Now, this assumption I made at the start that this is that these are P independent constraints, right? Assume independent. Assume that they're independent. That essentially means that these gradients of G1 through GP are linearly independent. It means that they form a basis for the normal space. Okay, so you put 1 and 2 together, what do you get? Independence of constraints implies that the normal space at P to M is actually the span of, let's say, P comma gradient G sub J of P, such that J is equal to 1, 2, P. And so you can write then, what's that say? That says that the gradient of F is equal to something like lambda 1 gradient of G1 plus lambda 2 gradient of G2 plus plus lambda P gradient of GP. At the extremal point, right? So if the constraint is if the constraint's a smooth surface, if the objective function is a smooth objective function, this is a necessary condition for the extremal point, right? But you should understand, at the start of all of this, we are assuming what? Yeah, that there is such a point, right? But hey, this gives you a method to search for it, right? Because we can all calculate gradients to functions and to constraints and set them equal and then look for these constants. And that's the method of Lagrange multipliers. Yeah.
So do you still find false?
Yes. You can find false positives. Let me see if I can find you an interesting example of that. Let's see here. So let's look at an example. See if I can make it interesting. My notes are there's some examples in the notes that I'm not super fond of. The totality of the examples in the notes are good, but let me see if I can come up with an example on the spot that's better. Let's suppose we're looking at the objective function f of xy. I'll keep it relatively simple. How about x? And let's look at the constraint function g of xy equal to y squared minus x squared, perhaps, equals to 1. Admittedly, this is a Lagrange multiplier problem we could have tried in calculus 3. Okay? So here we go. In this case, this is a problem in 2 dimensions, right? So the tangent space is 1-dimensional, the normal space is 1-dimensional to the constraint. The constraint is a curve. So the Lagrange multiplier technique just boils down to what? Gradient of f is equal to lambda gradient of g, right? So what's the gradient of f? 1, 0. Gradient of g is what? Minus 2x. And 2y. Yeah. So you got, you got to sell 1 is equal to minus 2 lambda x, and 0 is equal to 2 lambda y. So those are my Lagrange multiplier equations. Yes, sir? Lambda is the coefficient that you need to reach the gradient of the objective function as a scalar multiple of the constraint gradient. It expressed geometrically how the gradient to the objective function appears in the span of the basis to the normal space. It's just a scalar, though, is the Calc 3 answer. Scalar we don't know. I mean, we'll find it out soon. Actually, we don't care. It's an artifact. What we really care about is where the point where the maximum is found or minimum is found, right? So how you solve these equations here. And also, you always have to solve them subject to the constraint as well. Don't forget that. Y squared minus x squared is equal to 1. So these three nonlinear equations and three unknowns. The unknowns are lambda, x, and y. And those are your three equations. Generically speaking, it's beastly. But I think these ones we can hack through pretty easily. 0 is nice, right? What's that tell me? Either lambda is equal to 0 or y is equal to 0. But for this method to be interesting, we want lambda non-zero. Right? Yeah. Yeah, and exactly. And very good, Joe. The first one says lambda can't be 0 as well. Good point. Y has to be 0. And then if y is equal to 0, that implies that, come on. Okay, fine. Did I say 1? All right, Daniel, what should I do? There was a typo in the original statement of the problem. You'd like this example to be interesting, right? So let's put a minus there. Es bueno? Mi bueno. So y minus x squared is equal to minus 1, which tells me that x is equal to plus or minus 1. This is not complex analysis. I am not allowed such luxuries. We'll call it j. For me, j squared is equal to 1. You've been taught wrong. Oh? No. Your j squared is minus 1. My j squared is 1. It's not stupid.
What about the quaternion j?
Different j.
Quaternion j is squared root of thing.
Yeah, that's true. I will not be distracted. So, okay, so what we just found is that we have two extremal points, right? We have 1, 0, and we have minus 1, 0. Those are the points which satisfy a Lagrange multiplier condition, right? And so if you look at f of 1, 0, what do you get? 1, right? And if you look at f of minus 1, 0, what do you get? Minus 1, right? So, again, I was trying to give you an example of a false positive. So, if we blindly follow the Lagrange multiplier technique as if it just makes sense without regard to context and circumstance, and there's no extra thinking involved, we're like, aha, I have proved that this is the maximum, right? And this is the minimum, right? Wrong. Very wrong. Because now let me just bring us back down to reality here. What's the problem? What is the constraint curve? What is, so to rewrite it, that's x squared minus y squared equals to 1, right? That's a hyperbola that opens sideways. The constraint curve looks like this. So these points, right? That's 1, 0. That's minus 1, 0. Now, what are the level curves of the objective function? If I look at f equals to a constant, that would give me the contours of the objective function. What are the contours of the objective function here? I'll draw them green. No. If I look at this equals to a constant, this will give me, level of objective function. X equal to a constant, right? They're vertical lines, so. Oops. Well, I mean, you can't draw too many, but here's a few. My green is gradually becoming ungreen as I pass through the other colors. But of course, the gradient of f is just x hat, right? I mean, and so what you have is at these 2 points, you can see why we're able to solve this. That's where the gradient of f is like this, right? But which direction does nabla g point? So nabla g points like it's fine. It points like this, right? Or over here it points actually this way. So at these 2 points, the gradient of f and the gradient of g lined up. That's why we were able to solve the Lagrange multiplier equations. And yet, quite clearly, those are not the maximum and minimum values for f, right? Because you could f is just the x coordinate, right? So as you trace down the hyperbola, you keep going and going, x is unbounded that way, and x is unbounded in the negative way that way, right? So x goes to plus or minus infinity as you trace out the constraint curve. Oops. The Lagrange multiplier method apparently needs some qualification, right? What's the danger of the example here? What makes it? Let me do another example which works, and then we'll talk about the distinction between this first example and the example that works. How about that?
I mean, obviously, looking at them, you do go off into the short phase. But if you look at it from the side perspective, so essentially turn it this way, and then you would get, and then looking at it locally to those 2 points, I mean, it still found something. It's found points that have either 0 or an infinite slopes tangent.
There is something interesting about those points, right? But they're not global extrema, is my point.
Okay. Still useful?
I don't know. How do you define useful?
I don't know. So I'm trying to figure out the point of it.
The point is to find the minimum and maximum of an objective function subject to some constraint. What's that? It allows you to solve nonlinear optimization problems. I mean,
No,
hey. How about this? You've got a line. Let's say y is equal to mx plus b. You've got a circle. All right. I don't know. X minus h squared plus y minus k squared equals to r squared. Find the point on the circle which is closest to the point on the line. Now, geometrically, you can solve it. You kind of know what's going on here, right? You find a perpendicular line to the line, and you make it cut through the center of the circle. Geometrically, that's going to be the solution, right? No? Yeah? I'm not sure this is the example I want, though. Oh, man. I'm sorry, guys. I'm getting carried away here. I've got this up here. No, I'm going to have to erase it. I'm sorry. I forgot. I'm trying to show a point. I'm not trying to do an interesting. This is an interesting example. Oh well, it happened. Let's do a less interesting example. How about this? F of xy, and we'll just to keep it easy for class, f of xy equal to x, and let's look at g of xy equal to x squared plus y squared equals to 1. This is a really simple example, but it'll serve to illustrate the method quickly without wasting a lot of our time. So this is the objective, right? Here's the constraint. And let's see, same song and dance, gradient of f equals to lambda gradient of g. What's this give me this time? So I get three equations, right? I get 1 is equal to 2 lambda x. I get 0 is equal to 2 lambda y. And of course, I get my constraint. So I got these three equations and three unknowns I got to solve. All right? Yeah, the algebra is almost the same. Yeah, you said y is equal to 0. Again, lambda can't be 0. So y equal to 0, which then implies x is equal to what? Okay. So our points that the analysis found for us are 1, 0, and minus 1, 0. What happens when we feed these to f? F of 1, 0 is what? 1, yeah. F of minus 1, 0, minus 1. Okay, this is... Calc 3 should be so lucky that I put this on their test, right? But how many students would have the confidence to just write the answer down as I wrote the problem? How many people would foolishly try to work through the method without understanding?
I just wanted to make a test where every single answer was B except for the last one.
B? It's just all B's?
Every single answer.
And I'm very disappointed in you, Joe. I would have expected that the answer would have been 7 all around.
Say it's math. You have to be open-ended, so you can get 7. You have to be 7.
I worked an inordinate number of 42s into my business calculus test last week to mess with them.
You take a psychology class, right?
Mm-hmm.
Give them a 100-question multiple choice test.
Uh-huh.
Make every single answer B, except for the last one, and it's C.
Oh, 100 question multiple choice, all B's except for the last one being C.
And now, right? See what this does. It looks for the students who are looking for the pattern. It looks for the students that are actually reading every question. It looks for the students that are sitting there, seeing that every single one's B, and then can't possibly fathom that every single answer is B, and just have to put different answers, even though.
Yeah, that would be fun. This is why I should never teach psychology.
Yeah, that's why you should mess with psychology.
Okay, so again, just to recap, false, right? That is false. This, on the other hand, is true. That is the max, that is the min. What's the difference in these examples?
The first one's not compact.
Exactly. So the constraint, the difference is in the topology of the constraint. The topology of the constraint. In particular, my first example, the constraint curve was a hyperbola. This is not compact. You cannot put a finite open disk around it that will contain the whole curve, right? It's not compact. It's not closed and bounded. In Rn, compact is synonymous with closed and bounded, right? Something you would prove in real analysis if real analysis was done in n dimensions, but it's not. Anyway, you'll prove the one-dimensional analog of that, so we'll be content with that, and then I'm telling you now. So compact is closed and bounded in Rn. Now here, the constraint was a circle, right? Is a circle closed and bounded? Well, yeah, it is. And there's a theorem, and the theorem says this. If f is a continuous function from a compact domain, and I should be clear, it's a continuous real valued function, okay? So the range of the function is real numbers, okay? Codomain is real numbers. If it's a continuous function from a compact domain, then f attains its min and max at at least some point in the domain. I mean, it could be the same point. You could have the stupid example. It's a constant function that's continuous, right? So it could be attaining the minimum and the maximum at every single stupid point in the domain. That's possible. What?
What's compact mean again?
Compact means closed and bounded. So examples of curves which, so a circle is a compact domain because I can put this disk around it, right? And it's closed because the complement of the circle is the plane with the circle removed, and that's an open set because every point is interior if you look at the complement to the circle. An example of a curve which is bounded but not closed would be something like, suppose you take the circle, remove a point, right? Well, that would be problematic because the complement to this set is what? It's like that point, right? And then that removed everything else. That's not open because of that point. So a circle with a point removed is not compact. And that point being removed is the problem. That could be where the min and max is. And that's why the theorem fails.
You said, like you said, for that one over there, the reason why it doesn't work is because X is unbounded.
Right. Well, not because X unbounded is the failing. The reason it fails is because the hyperbola is not compact. So it fails to meet the condition of a compact domain. Okay. I was about to say something. Oh, man. What was I going to say? Curses. Go ahead, ask questions.
In higher dimensions, we would determine that the set is a compact domain by if it's open or closed plus something else.
Well, generically speaking, compact is defined as if every open cover admits a finite subcover, it's said to be compact. So that means that you've got this set of sets which covers the space, and then you can find a sub-selection of those that covers the entire space, which is finite. That's what you get for that's the abstract definition of compact. And I do think it's still true that this theorem exists for abstract topological spaces. But if the set is a subset of Rn, then compact again is interchangeable with closed and bounded.
So closed means that you can draw an open ball around it, and bounded means that no point is missing from it.
Other way around. Closed meaning that the complement of the set is open. Bounded meaning that you can find an open ball that is around it and the whole thing fits inside. Basically, you can pick some center point and then draw, lines of a fixed different distance from that center point, and the whole thing will be inside that. Now, this theorem is you've seen this in Calculus 1, it's called the extreme value theorem. You look at sometimes it's called the closed method, the closed interval test. You have a continuous function from closed interval a to b, and you can check the endpoints, f of a, f of b, and then you look for where f prime of a is equal to 0 in the middle, right? And at one of those three things, there has to be the maximum, there has to be the minimum. That's an application it's a specific instance of this general theorem, because the closed interval on the real line it's a compact set on the real line. So you've been exposed to this theorem in Calculus 1. It's the extreme value theorem. This is just the generalized extreme value theorem. So in order to be sure that the Lagrange multiplier method is going to work out nicely and that you're not looking at false solutions, you need the compactness of the domain. That said, we still will try Lagrange multiplier problems for non-compact problems. We just have to be careful then to double check our answers as actually being legitimate. All right? So it's just a caveat that you have to be careful. If you're going to try to apply the method of Lagrange multipliers outside a compact domain, well, watch your back. Make sense?
It's not necessarily wrong. It's not.
Yeah, exactly. These were wrong.
Right.
But I think the problem I was just about to work over there with the circle and the line, I think that would be an example of a non-compact. The line is not compact. It goes on and on, right? So I can look at the set of points in 4 dimensions, which puts you on the circle and the line in 2 dimensions. that will be a non-compact domain, and we'll still be able to reasonably solve the problem. I'll show you. Although my spider sense is tingling, and I do believe I'm going to replace that problem with a more explicit problem as to not waste the rest of the class fighting with H's and K's and stuff. So I'll try to make it at least a little bit interesting, though. My spider sense, yes. Danger, you know.
Even if it fails, does it failing mean that we found a point that has an infinite slopes table?
It failing can mean an infinity of different things. I have no idea. I mean, let me show you. I mean, these problems are misleading. This method is far more general. So, for example, take the line y is equal to x plus 1. We'll do that. And take the, let's see here. Let me take the circle over here centered at, I don't know, 3, radius 1. Question. Find point on circle and point on line closest. In other words, find the distance between the circle and line. Now, again, geometrically, I think you already know the answer, right? But I want to use this as a showcase of the method. Okay? So here's the thing. This is a problem in 2 dimensions, right? But it's really a 4-dimensional problem. Let me show you why. If I take this point as, let's say, xy, I don't really want to also take this point as xy, right? I should call it something else. A and B, U and V. What do you guys want? 7 and 8 is not an option. No! Very consistent. Comedy is very, very consistent. I will give you that. Let's see here. And so what you're trying to minimize. Bad choice in labeling. You're trying to minimize this distance, right? But as we all know from our previous experience with optimization, it's better to minimize the distance squared. So our objective function, right? Our objective function is a function of x, y, a, and b. This is a problem brought to us by 2 dimensions, but a 4-dimensional approach is warranted. Because you need 4 dimensions to put both the circle and the line basically independently. And so, but what we're trying to minimize is what? It's x minus a squared plus y minus b squared, right? That's the distance between these 2 points squared. And that's subject to what constraint? So I want, let's say, g of x, y, a, b equals to what? This is a 4 dimension, right? I need 2 constraints, right? Yeah. So okay. So how do you guys want me to look at this? Y minus x. Okay. And then what's the circle's what? What's the equation of the circle in a and b? It is a minus 3 squared plus b squared equals 2. 1 apparently, right? So I can have I made this up. Key is not preparing. Okay. It's kind of depressing for me. Like I can't really write that on, like, you know, you have some faculty portfolio. Talk about your teaching this year. Talk about your strengths and weaknesses. How should you do? Blah blah blah. Well, I found that I really should not prepare for class. It's the best thing. They'll never believe me. Right? Well, that is of course That is, of course, true, and it's also obvious from the other variety of incorrect things I should never have said on the form that I've already said. Adaptability. Okay, so down here, we want to, so this is like G1, this is like G2, right? And so we want to solve the gradient of f is equal to lambda 1 gradient of G1 plus lambda 2 gradient of G2 in this case. So what is that? That is 2 times x minus a, 2 times y minus b, minus 2 times x minus a, comma, minus 2 times y minus b. Now what have I done? Yeah, I'm taking the viewpoint that we're working with R4 with variables x, y, a, b. This notation is super handy. This is saying I'm working with R4, and I've denoted the coordinates on R4, x, y, a, b. So like the first thing is partial x, second thing's partial y, third thing's partial a, fourth thing's partial b in my notation here. You got choices. You could put a and b first and x and y second if you wanted to, right? Now that's lambda 1 times what? So the G1, this is G1, right? This is G2. So G1 is pretty, I mean, it's what? It's negative 1, 0, 0, 0. Oh, yeah, sorry. At least you guys are paying attention. That's good. See, I planned that before class for your learning. Bask in the blinding light of my pedagogy. Okay. I use the word pedagogy. That means I'm an educator. Sorry. Pedagogy, if you hear a student using the word pedagogy, it means that they're filling out a student evaluation. They just read the word and they're using it again. Okay, so 0, 0. I never hear students talking about learning style until student evaluations. It's funny. It's almost like it's because they're parroting back what they just read in a question. Let's see here. So this is 2 times a minus 3 and 2b. No Shakespeare's in my class. Let's see here. Yes, I know. If I had made it 7. And so then you've got these lovely equations to solve. You've got 2 times x minus a is equal to minus lambda 1. You've got 2 times y minus b is equal to lambda 1. You've got minus 2 times x minus a is equal to 2 lambda 2 times a minus 3. You've got minus 2 times y minus b is equal to, starting to regret doing this problem, 2 lambda 2 times b. And of course, all of this is subject to what? Yeah, y minus x equals to 1. And of course, our old friend, a minus 3 squared plus b squared equals to 1. All right, there you go. Six equations, 6 unknowns, nonlinear. Can we solve them? So the Lagrange multipliers, they're the star, but yet we don't care about them, so eliminate them. I mean, get rid of the Lagrange multipliers if you can. So I take these two, and that gives me that x minus a is equal to y minus b, which seems kind of handy. Call that equation 1. What's these two give me what? Lambda 2 is what? Lambda 2 is equal to, I don't care what it is, but it is equal to indeed I am. Thank you. B minus y there. Better? Now, lambda 2 is, we can cancel the 2's, right? So lambda 2 is, on the one hand, it's x minus a over a minus 3. And that's equal to what? Oh, thank you. I keep forgetting that minus. B minus y. Sorry, I sprang on the board. Over b. 2. Yeah. A minus x, you say?
Yeah.
Okay. Now we're good?
Negative math equation as well. Granted, you can flip both of them back.
Yeah, yeah. We got choices.
The way that you want to do it.
I think I'm going to go back to x minus a.
And y minus b.
Yeah, and the reason for that is just so I can more easily see what to do in the next step. Okay. Right, so this tells us what? So you combine 1 and 2. 1 and 2, put them together. What do we get? See, I've got that x minus a is equal to minus. So I can basically, I got b minus y over a minus 3 is equal to y minus b over b, right? Which tells me then that 3 minus a is equal to b. Of course, a equals to 3 is an exceptional case, right? I divided by a minus 3 means I probably should look at a equals to 3 separately. Then what? Then you feed it back to this, right? So that tells me that b squared plus b squared is equal to 1 because the square eats the minus. And so b is equal to, 2b squared is equal to 1. So, or b squared is equal to 1/2 is probably better. So therefore, b is equal to plus or minus 1 over the square root of 2. And then what? Why are there so many people coming in and out of here? It's still like almost 20, it's more than 20 minutes till the end of class. Like, why is there so much traffic through here right now? It's weird, right?
There's some school business.
Business. No, I hate them. Sorry. Just kidding. We love business. What's that? Hmm? I don't understand what you guys just said. I'm sorry. Oh, okay. So b is plus or minus 1/2. Then how do you find a?
B gives you a 4.
So what's that say a is equal to? Three minus plus 1 over the square root of 2. And then what's x and y then?
2 and 3 give you y. Or 1 and 2 combined give you y from a and b. And then 3 gives you back to equation 1.
Oh, so we get x plus y. X plus y is equal to b minus a? What? Oh, thank you. Yeah, b plus a. What's b plus a here? Yeah, very good. But on the other hand, x plus y is equal to what? Oh, well, I guess I can't use that. But now I've got x plus y is equal to 3. And I've also got that y minus x is equal to 1. So if I add those, that gives me 2y is equal to 4. So therefore, y is equal to 2. And x is equal to 1, right?
Couldn't b plus a also equal 3 plus square root of 2?
But the plus or minuses are juxtaposed, so they cancel.
Oh, they're always.
This is on purpose. That minus goes with that plus. So that's the, yeah. Have you ever seen this notation before? So here's a great use of it. Cosine of theta plus or minus beta is equal to, get this, cosine theta, cosine beta, minus plus sine theta, sine beta. So this notation, the way it works is the plus, it's oriented. I mean, this plus goes with the minus, and the minus goes with the plus.
Two separate equations.
Yeah, yeah. Anyway, so notational jubilation aside, what's the answer? So we found that the point 1, 2 on line closest to, what was it, a, oh, actually not closest, right? So we've got 3, let's say we got 3 minus 1 over the square root of 2, comma 1 over square root of 2, or what was it, 3 plus 1 over the square root of 2, comma minus 1 over square root of 2, right? One of these is the closest point, one of these is the furthest point from, now, and here's an example of the non-compactness misleading us, right? One of these answers is indeed the closest point. The other one is, of course, not the furthest point. Geometrically, you can see that from the start of all this, right? I'll do it over here. So if you think about the answer, right, here's my line, here's my circle, and, you know, see what this analysis just found for us was the honest to goodness closest point right there, right? But also this false positive, right? I mean, is not the farthest point, right? Certainly not. I mean, if I just pick any point on the circle, I can find points on the line arbitrarily far away. So there is no furthest point. I mean, but that is the pair of points which are closest.
Would it be like the farthest point?
Which one is? I think it should be. It should be this one, right? This is the closest point. Yeah. I can see that geometrically, but what's that?
I was asking a question, but I'm not sure.
Oh, okay. Mm-hmm.
What I think he's asking is the false positive we found the point on the circle that is furthest from the line?
Yes. I mean that would be this guy, right?
So we're not so much looking at like the closest 2 points. We're actually looking distinctly at the circle that is furthest from the line.
Yeah. Well, I mean, going back to the objective function, right? If you plug those points into the objective function, I'm arguing that if you go back to here and plug this in, plug the points into that f we had, one of the values would be larger, one of them would be smaller. The one that's smaller does actually correspond to the closest point of the circle to the line. The one that's larger, it's not actually the point on the circle which is furthest from the line. There is no point on the circle which is furthest from the line. That question doesn't make sense. I mean, in order for the distance between we define the distance between two extended objects to be the smallest distance, right?
So you're saying it's like based on the point, like.
If you want to talk about the farthest distance, between the point and the line, the line goes on and on. I mean, there is no.
So if the line was bounded, then it would be fine.
Yes, if we had a line segment, different ball game.
Then that would satisfy the constraints. Bounded.
Yeah, that would be ooh. Yeah, this problem with a line segment is nasty.
So if we take
Because then you have to think about, for the line segment, which point on the circle is furthest from the line segment, right?
You couldn't just assume that it's going to be the endpoint of the line segment.
I don't know. If it was a line segment, I haven't worked this problem with a line segment. I'd have to think about it.
So you're saying like that based on the point like 1, 2 on the line, that's why it gives us the other dot, basically because that's the point on the circle that's farthest away from the dot that was one from the line. confused that sounds?
Yes.
Okay, okay.
It's the other place where the gradient, yeah. Now, in Edwards, if you read, he does this problem for essentially arbitrary, like an arbitrary objective function and an arbitrary constraint surface in an Rn, and basically shows that the answer is where the gradients line up, which is what we found. The gradient to this will be like perpendicular. The gradient to that will be perpendicular. We found the points where the gradients line up if you parallel translate one to the other. This is, I mean, he has that Uber example in Edwards. If you find, I forget the number, but it's in there. So anyway, I just wanted to show you this is the method of Lagrange multipliers. And so if you want to solve where is a function largest subject to like some constraint curve or some constraint surface, or more generally some constraint manifold, this is the tool to use, right? But what this doesn't answer is if you've got like some open set, right? Where is the function largest or smallest in an open set? So, you know, here's a typical problem. Let me show you what I'm talking about. Suppose you wanted to find the minimum and maximum values of some constraint. Let's just talk about a function of two variables because we can draw pictures better there. You probably worked this problem or problems like it in Calculus 3, right? But the next class of problems we want to look at is something like this. Find the maximum for a function from D, some subset of R2, let's say to R. And let's suppose D looks something like, I don't know, this, whatever. Here's D. So my point is D is not just a curve. It's actually, you know, there's two parts to D. You can write D as equal to, let's say, the interior unioned with the boundary of D. So the boundary of D, this right here, is a curve, right? So if I want to find where is F, I could write that, of course, as like G of xy equals to some constant, right? And if I wanted to find where is F the largest on that curve, well, we talked about that today. You could use the method of Lagrange multipliers if you wanted to, right? And you could find where the gradient of F matches the gradient of G and solve the Lagrange multiplier problem. Or, alternatively, less high tech, you could just parameterize the boundary curve as a function of time and directly maximize the function evaluated at the parameterization of the boundary curve. That's also a valid method, right? And that would give you the maximum of the function, the objective function, on the boundary. But you see, there's also this inside, right? There's the interior of D. And how do you find out where the function's largest and smallest in there? How does that work? Right? So the next question is, how do we locate and analyze local extrema for a function, right, of two variables? But of course, I'm not content with two variables in here. I'm going to show you how to do it for n. Yep.
So we're saying that only local extrema could exist inside the surface? Like there couldn't be an absolute extrema inside the surface?
A local extrema could be an absolute extrema, sure. That just means it's also, if it's absolute, it's also the largest on the set in consideration.
So you don't have to be on the boundary of the surface to be an absolute?
No, the absolute extrema could happen on the boundary or in the interior in general, yeah. So do you guys remember the story from Calculus 3? What was the result? You have to look for the critical points in the interior, right? Or maybe you would call them stable points. They're points where the gradient of F is 0. Okay? So it turns out that the criteria for this is just that the gradient of F at the point P is equal to, 0, 0. And so if you were just interested in sort of a generalized closed interval method, that would be all you needed. You just find the critical points, you evaluate the function at the critical points, and then you compare it to the possible maximums on the boundary,